Hi, welcome back to Organic Chemistry. We're continuing on with our discussion of alkenes, and here in our fourth installment out of four, we are finishing up our discussion of the reactions of alkenes. If you haven't seen the previous sections of this video, sections 1, 2, and 3, you might want to go back and look at those, as this will just continue on exactly where I left off and assume you already went through that material. Remind us where we're at. I'm dividing up the reactions of alkenes into four fundamental types. We have already gone through electrophilic addition reactions. These are where the pi bond reaches out to an electrophile, there's some sort of carbocation intermediate, and then a nucleophile comes along to get a net addition of an electrophile and a nucleophile. We went through several different examples of different electrophiles and nucleophiles, including considerations of regio and stereo selectivity. We're going to continue on looking at, in this section, at cyclopropanation, etc. That is a couple of reactions that make triangles. Cycloaddition, reactions that, at least in their first step, make rings of other sizes. And reductions. Now I want to point out that the first three major types, as I'm classing them, electrophilic addition, cyclopropanation, etc., and cycloaddition, are all related to each other, at least in their first step, at a very fundamental level. Reductions are going to be a completely separate type of mechanism, distinct from these others. All right, let's proceed on. All right. That's electrophilic addition, which is really the main reaction type of alkenes. We're going to go through three more reaction types. For instance, cyclopropanation, etc. Okay. If I treat an alkene with diazomethane, we'll talk about what that is in just a moment, I will make a three-membered ring, a cyclopropane. So here's an example. The intermediate that's going to be important in this, the reactive intermediate, is a carbene. A carbene is an odd species. It's highly reactive because this is a reactive intermediate that only has 6 electrons around a carbon. So it doesn't have an octet at all. It's neutral because the formal charge on carbon is equal to the number of electrons you start with in a neutral atom, the number of valence electrons, that's 4, minus the number of bonds, minus the number of non-bonded electrons. So this is net neutral, but it doesn't have a full octet, so it's very reactive. It's even more reactive than a carbocation or a carbanion. If you were to think about the structure of CH2, neutral CH2, the carbene, this species, you would realize very quickly that it's going to have a trigonal planar array because we've got 2 CH bonds and then we got a lone pair. And the best way to arrange those is at 120 degrees to each other. That's an sp2 hybridized carbon. Okay, if I had an sp2 hybridized carbon, I got 3 sp2 orbitals. 2 of them are going to be involved in CH bonds. And then there's this, the other sp2, and then a p orbital. If I was to fill in the electrons, of course my bonds, I've kind of established those already, but these 2 electrons are going to end up in that sp2 orbital, and the p orbital is going to end up empty for a singlet carbene. And this singlet carbene is kind of weird, because if I only looked at one part, it's got a lone pair. If I only look at this orbital, it's got an empty p orbital. Carbons with lone pairs are carbanions. Usually when we think of a carbon with a lone pair, we're thinking of a carbanion. Carbons with empty p orbitals, when we think of those, we're thinking about carbocations usually. These carbenes are weird because they behave as if they are kind of both a carbocation and a carbanion simultaneously. So there's net no charge, but they're going to be very reactive species. They're going to act as both electron pair acceptors and electron pair donors. Okay, where do we get them from in the first place? Probably the simplest way is to take diazomethane, CH2N2, and here's one resonance form of diazomethane, but here's another. And if I look at this resonance form of diazomethane, and I imagine breaking that bond, if I broke that bond, what do I make? I make N2, like if these 2 electrons go to nitrogen. what's going to blow away is N2, and that's a big proportion of the stuff you're surrounded with every moment of your life, right? The atmosphere, the primary component of the air around us, is nitrogen gas. Nitrogen is extremely stable, and if I can break off a small molecule that's very stable, that's going to be a favorable thing mechanistically. We've seen that before in reactions where we had water act as a leaving group. We broke a bond and we made a small, stable molecule as leaving group. Well, here, nitrogen is like the world's best leaving group, because what leaves is this completely neutral, completely inert molecule. So thermodynamically, breaking that bond and blowing off N2 is going to be a very favorable thing, very much downhill. But if you do break that bond, this carbon, this, it's got a lone pair here, but if I take away those 2 electrons, now I've got a carbene. Okay. There are other ways to make carbenes as well. For instance, I could take CHCl3, that's chloroform. If I were to deprotonate with a strong enough base, so say I treat chloroform with butyllithium, I'm going to pull off that hydrogen to make a carbanion. So I do need a very strong base to do this, but I can do it like if I treat it with butyllithium, because this carbanion is more stable than the carbanion in butyllithium. But it's a carbanion, and so it's going to be reactive, and it would like to get to neutral, and one way it gets to neutral is by ejecting a chloride ion, a Cl, with its 2 electrons. And the result is dichlorocarbene. So we can make carbenes in a couple of ways. There are other things that behave a lot like carbenes. There are metal carbene species or carbenoid species. For instance, if I treated a gem diiodide with zinc, I would make something that behaves a heck of a lot like a carbene. It's not exactly a carbene, but the net result is indistinguishable from the net result in these top 2 cases. Alright, so let's go back to our reaction. If I was to treat an alkene with diazomethane, and I generally have to add in a little bit of heat or a little bit of light, but diazomethane is an extremely reactive compound. In fact, it's kind of dangerous to work with if you don't use proper techniques, because it can be an explosive because it is so reactive. A reaction will occur to make a cyclopropane. Now, how does this work? Let's imagine this stepwise. Okay, this is a lie. We'll come back to the real mechanism in just a moment. But remember, we said a carbene has both the properties of an electron pair acceptor, that is, it's got an empty p orbital, and an electron pair donor, that is, it's got that lone pair in an sp2 orbital. But we know that pi bonds want to reach out to good electron pair accept, good Lewis acids. And so we could imagine a pi bond reaching out to that carbon to make a bond, leaving behind a carbocation intermediate. But in this case, the carbon I was reaching out to had both an empty orbital and a filled orbital. And so we would, if we imagine doing this stepwise, we would make a species, a zwitterion, right, because there's a plus and a minus in the same molecule, where I've got a negatively charged carbon and then I've got a carbocation here. And if I had this, imagine in kind of a thought experiment that we just had this molecule, that would be very quickly reach around to react with itself. That is, if this carbon reaches out to make a connection here, we'd see our observed product. Now that's a lie. This reaction does not take place in 2 steps. It actually happens all at once. That is, the pi bond reaches out to the empty orbital of the carbene, and at the same time, the filled orbital, the lone pair, reaches back to the other end of the pi bond. By the way, when you see these brackets with this little symbol here, that means the transition state looks something kind of like this. That is, this carbon is interacting with both of these carbons at the transition state. All right. Epoxidation is a very similar reaction. Notice it also makes a 3-membered ring. But in this case, the 3-membered ring isn't just 3 carbons, it's 2 carbons and an oxygen. So if I start with an alkene, and I treat it with a peroxy acid, we'll get to what that is in just a moment, I will make an epoxide. Epoxide is the name of a 3-membered ring comprised of 2 carbons and 1 oxygen. That peroxy acid, RCO CO3H, you're used to CO2H, a carboxylic acid. If I was to add one extra oxygen, I'd get a peroxyacid. So generally speaking, these things are anything with this general structure of a CO double bond, and then an O, and then an O, and then an H. One of the most commonly used peroxyacids is MCPBA. It's got a benzene ring. It's got a chlorine at the meta position. That's 2 carbons over. And here it's got the CO double bond, the O, and the O, and the H, just like we showed over here. All right. If I treat an alkene with a peroxyacid, and let's imagine this goes in a stepwise fashion. Oxygen-oxygen bonds are kind of weird. Usually, in mechanisms, we have seen an oxygen act as an electron pair donor. But if I've got an oxygen-oxygen bond, these lone pairs repel each other, and it's going to be very easy to break this bond and push 2 electrons onto this oxygen. But to do that, we have to have something share electrons with this oxygen, because oxygen, being so highly electronegative, doesn't want to have fewer than 8 electrons around it. So let's imagine a pi bond reaching out to oxygen, simultaneously breaking a bond between oxygen and oxygen to make a carboxylate, the conjugate base of a carboxylic acid, as the initial product. And I can show that that's resonance stabilized. So here's the resonance form. I guess I should have used resonance arrows. But I could show this form that puts the minus charge on this oxygen. And, you know, that oxygen would like to not be charged, so you could imagine it reaching out and grabbing a hydrogen to make a carboxylic acid as your byproduct, and that is the true byproduct of the epoxidation forming reaction, the epoxide forming reaction. But here we've got an O minus, and right here a carbon plus. And so you might imagine these are going to get together. Alright, so here's the stepwise mechanism, but it doesn't really happen stepwise. In reality, it all happens simultaneously. The pi bond reaches out to the oxygen, electrons swing to here, electrons swing back over here and pick up a hydrogen, and these electrons go back to the carbon. And this all happens in one transition state. That is, it all happens simultaneously. Notice in both this case and the cyclopropanation, one atom is acting as both electron pair acceptor and electron pair donor. In this case, notice that we make a bond from the pi bond to this oxygen, and we make another sigma bond when this oxygen reaches back to this carbon here. The transition state looks something like this, where all of those bond changes are happening simultaneously. Both of these reactions, the cyclopropanation and the epoxidation, happen in a syn fashion. They have to because the same atom is acting as both electron acceptor and electron donor, and it's simultaneously interacting with each end of the pi bond. And so it either has to be in front of the page or behind the page. But it can't be simultaneously, in both in front and behind the page. Here I show a couple of other examples where stereochemistry of starting material is preserved in the product because that either carbene or epoxide approach has to be from one side of the alkene at a time. And since it all happens at once, both bonds have to be formed on the same side of the carbon. All right, let's dig into our third set of reactions of alkenes. And those are reactions that start with a cycloaddition. I say start with the cycloaddition because at least the first two examples I'm going to show have a part B that we're not going to focus on the mechanism of, though I will show them. That's important to getting to the overall product. What I want to focus on the mechanism of is the first step. Because in each cases, the first step look very similar. With ozone, osmium tetroxide, and butadiene, pi bond is going to reach out and interact with one end of this molecule. We're going to move some electrons internally, and then a pair of electrons is going to come from the other end of the molecule back to the pi bond. So notice in each of these cases, I simultaneously make connections with each end of either a 3 or a 4 atom piece. And of course the product that happens if I connect to each end is a cyclo. In this case, a dimethyl cyclohexene. In this case, well, we'll see the products of this and this shortly. So let's take the ozone case. Lie. If I had ozone and an alkene, you could imagine the pi bond reaching out to ozone. Because this ozone's got a positive charge here, so you can imagine it acting as an electron pair acceptor, and it does. Of course, oxygen can only have 8 electrons around it, so let's shift 2 electrons to this positively charged oxygen, so now it's neutral. And at the same time, we have this oxygen that wants to share electron density with somebody, and in the process of that first bond formation, we form a carbon blanked for there for a second. A second carbon oxygen to make a ring. Now, really it happens in a concerted fashion. It doesn't happen in 2 separate steps. But overall, what happened? The pi bond reached out to one end of this molecule that was acting as the electrophile, the electron acceptor, and then the other end of this molecule comes back and acts as nucleophile, adding to the other end of the carbon-carbon double bond. And it all happens simultaneously, but it's still following that same motif of pi bond reaches out to electrophile, and nucleophile comes back to the other end of the pi bond. It's just in this case, and in other cycloadditions, the electrophile and nucleophile are 2 ends of the same molecule. I am just going to show you the rest of the story. I'm not going to go through it in detail. I'm not going to hold you responsible for it. I will hold you responsible for knowing the overall net product of ozonolysis. But you initially form this ring. This ring is relatively unstable because it has 2 in a row oxygen-oxygen sigma bonds. And I said on that a little bit ago that oxygen-oxygen sigma bonds are relatively easy to break because the lone pair on this oxygen and the lone pair on this oxygen repel each other. And that's going to help break this bond. And that we could break this thing apart and make these 2 species. Of course, I could bring these back together and make this, so there's going to be an equilibrium, but it's really going to favor this side. But these species can come together in 2 different ways. They could either come together making a connection between these 2 oxygens and these 2 carbons, and that would be this product, or this would be the product of that transformation. Or I could have the oxygen from this piece react with the carbon end of this CO double bond, and the other end goes back to the other end of this carbon-oxygen pi bond. If I did that, I would make what's called the secondary ozonide. This, by the way, that was the primary ozonide, a different 5-membered ring. This one's still got an oxygen-oxygen bond, so it's relatively reactive, but it's more stable than this first one. And this one would actually stick around for a bit in solution. And so what we would do in an experimental setting is we would first add the borane, let things stir for some specified amount of time. And then we would add dimethyl sulfide. So here I show what happens when you add dimethyl sulfide to the secondary ozonide. Sulfur reaches out to oxygen, breaks a bond between oxygen and oxygen, but those 2 electrons have to go somewhere. Let's put them here. If this thing breaks apart, with the help of sulfur, what we're going to do, sulfur is going to reach out to here, we're going to break this bond, make a CO double bond break this bond, where do those electrons go? They're going to come over here to make a CO double bond. And then that's going to put extra electron density here. Sorry. If I make a CO double bond here, there's an implicit hydrogen here, so there's already 8 electrons around here. So if I make a bond here, I'm going to have to break a bond. Let's break this bond and have those go to oxygen. All right. The net results was that our initial alkene got chopped in half to make 2 aldehydes. The other cycloaddition reactions at least start out the same way. So if I treat an alkene with osmium tetraoxide followed by aqueous base, a reaction will occur that starts out with another cycloaddition reaction. My carbon-carbon pi bond reaches out to the oxygen end of an osmium-oxygen pi bond. Electrons from that pi bond go to osmium, and the other oxygen reaches back. Okay. So what happens next is hydroxides come along and end up breaking the bonds between osmium and oxygen. After protonation, you end up with OHs. I am not going to go through this in detail. Again, I won't hold you responsible for this mechanism, though it's pretty straightforward. I will hold you responsible for knowing the net overall transformation of alkene plus osmium tetraoxide will be this diol. All right. This dihydroxylation reaction has a specific sense of stereochemistry. That is, it goes with syn addition. The products, the two OHs in the product, ultimately are going to be on the same face of the pi bond, of what was initially a pi bond. Why? Because in the mechanism, bonds were formed between oxygen, these two oxygens, and these two carbons simultaneously. That is, there's one molecule of osmium tetroxide here that connects up simultaneously with each oxygen. The oxygens from osmium tetroxide simultaneously connect up with each carbon of the pi bond. The osmium tetroxide is either going to be in front of the board or from behind the board, or behind your computer screen, I suppose. Which means that you're either going to get both of our oxygens in front or both behind. And then when you break those osmium-oxygen bonds, you're going to end up with two OHs. They'll either be both in front or both behind. This will be true of cyclic alkenes, also acyclic alkenes. You will get a racemic mixture of this and the mirror image of this, but notice there are 4, when I've got 2 stereocenters, I could draw 4 stereoisomers. I'm either going to make this one or in the mirror image of this one. I'm not going to make the one where, say, this one's forward and that one's back. Of course, on the other hand, if I started with this alkene, I would make the one where this one's forward and this one's back, because my intermediate, well, first, my osmium comes up to this, and the oxygens either come from in front or behind. And then after I cleave the bond between oxygen and osmium, I have free rotation around this. And so if I just draw this rotamer, this conformation of this diol, it would look like this. Finally, I just want to point out that there are other variations on this reaction, and probably the most important for us is that this reaction can be done catalytically. Instead of using a lot of osmium, that is 1 mole of osmium for every 1 mole of your alkene, you could use a catalytic amount of osmium, and that's going to be good for green chemistry purposes, because osmium's a metal. You generally want to cut down on the amount of metals you're using, because they're generally have some level of toxicity. And so the less you use, the less waste you produce. So there's a catalytic variation on this that has osmium tetroxide, but then it throws in this NMO. And this NMO basically takes the reduced form of osmium, that's a byproduct of this reaction, and it reoxidizes it to make more osmium tetroxide. One final cycloaddition is the Diels-Alder. That is when I've got an alkene and I've got a diene, that is 2 pi bonds in a row. Pi bond can reach out to this end, electrons go here, and then electrons come back here to make a 6-membered ring. We're going to spend a lot of time on this in a subsequent unit when we talk about conjugated alkenes. All right. So here's the story so far. We have seen a lot of reactions where a pi bond interacts with an electrophile and a nucleophile. We saw reactions where the electrophile and nucleophile were things like HCl. The electrophile was H+, the nucleophile was chloride minus. Pi bond reaches out to electrophile, carbocation intermediate, nucleophile comes along. Yeah, there were some varieties on that, but they all came down to that. By the way, that gave you a kind of stereo random, because if my electrophile came from the front, my nucleophile could come from either the front or the back, so we'd actually get a mixture of stereoisomers. We also saw some examples where our electrophile was something that was very large and it had lone pairs. Specifically, we saw this when pi bond reached out to, say, Br2, or Br2 in the presence of water, or we could have done Cl2 or I2, the mercury case. In those cases, you form a bridging intermediate, and therefore the nucleophile, whatever it was, had to come from the opposite side. So we see examples where electrophile and nucleophile, but due to some details of the intermediate, the nucleophile comes from the opposite side. So these are very similar, just they've got to the top examples, but they've got some level of stereo control. We saw, well, hydroboration, where the electrophile and the nucleophile were directly connected, and that gave us an addition product that involved syn addition, where electrophile and nucleophile came from the same face. Again, specifically, here I'm thinking about borane, where our electrophile was the boron and our nucleophile was a hydrogen. We've seen examples where one atom acted as both electrophile and nucleophile, and this all happens simultaneously, but still, pi bond reaches out to electrophile and nucleophile reaches back to the other end. But if the same atom is both electrophile and nucleophile, we're making a 3-membered ring of necessity. We saw this with the cyclopropanation and the epoxidation. And then, last but not least, the cycloadditions involve the pi bond interacting with some molecule, where one end of the molecule acted as electrophile and the other end of that molecule acted as nucleophile. And so those we made some ring structure, at least in the initial step. Now there's one last form of, so let me step back. So we've seen 3 major types of reactions of alkenes. That is electrophilic addition, the cyclopropanation, etc., and the cycloadditions. But they all involve the same fundamental idea. Pi bond reaches out to something that's electrophilic. Sometimes you don't have an intermediate, but there's at least some positive charge buildup, and nucleophile adds back to the other side. That's very similar about all those. Now, on our initial slide summarizing alkene reactions, I said there's 4 types of reactions. And the last one is catalytic hydrogenation. If I treat an alkene with some palladium, though there's other metals that do this as well, platinum, nickel, etc., catalyst, a reaction will occur to add 2 hydrogen atoms. But this doesn't go by the same electrophilic addition. It is an addition, right? I'm going in this case from C6H10 to C6H12. So I'm adding atoms and I'm not taking any away. So it's an addition reaction, but it turns out it's not an electrophilic addition reaction. This one goes via a more radical reaction. We've seen this reaction before when we talked about the relative stabilities of alkenes earlier in this presentation. And this goes a different mechanism. That mechanism starts with a heterogeneous catalyst. A heterogeneous catalyst is one that is in a different phase than your reacting species. So pretty much most heterogeneous catalysts are solids, and they are catalyzing, that is, they're accelerating the reaction of some solution, some dissolved species. So when I talk about palladium catalyst, it's solid palladium, but it's actually a really, really fine dust. Okay, so it's a really small amount of solid palladium. But relative to individual molecules of organic, it still looks really big from their perspective, right? Okay, so let's imagine a chunk of solid palladium. And when that interacts with hydrogen gas, that will encourage the dissociation of hydrogen atoms to make things that I'm going to treat as essentially hydrogen radicals coating the surface of that solid palladium. Okay, so this is a bit of a simplification, but let's treat it like hydrogen radicals sitting on that surface. Now, if some alkene comes along, now this chunk of palladium, imagine this extending in each direction for some ways. This is going to be from this relative to a single molecule of, in this case, tetramethylethyline. This is going to be some huge chunk of palladium with the surface covered with hydrogen radicals. And if this alkene comes close by, we know that radicals do a relatively small number of things. They combine with other radicals, they do atom abstractions, or what's important here, they add to pi bonds. And so here, what's going to happen is as this alkene approaches the surface covered with hydrogen radicals, a reaction can occur where one of those hydrogen radicals reacts with that pi bond. Now we know the result of that mechanistic step is a carbon-centered radical. And that, in our scheme, is sitting right next to this surface, which is covered with hydrogen radicals. And one of the other things that radicals do, which is an extremely favorable thing thermodynamically, is they combine with other radicals. And so this carbon-centered radical is sitting right next to a hydrogen-centered radical, and so a reaction can occur. This will necessarily, well, no, let me step back from saying that. This reaction is stepwise. It is not a simultaneous addition of two hydrogens to the alkene. So at least in theory, you could get a mixture of stereoisomers, but in reality you don't. In reality, you will get 99.99% syn addition, and the reason for that is to get anti-addition, what would have to happen is this molecule would have to float up away from the surface, flip over, and then float back down to the surface, and have it interact with a hydrogen on the other face. But since this second step is so rapid, this is going to give you really syn addition. Because as this pi bond approaches this big thing, it's like coming down across, like, I don't know, an aircraft carrier, and the face of this pi bond will interact very rapidly with two hydrogen radicals that have to be coming from the same face. They can't have one coming from this face and one coming from up here. All right, that's the reactions of alkenes. Alkenes essentially do four things. They do electrophilic addition. Okay, we saw some flavors of that. But things like HCl or HBr or acid and water. We saw flavors where, like borane, where our electrophile was a boron instead of a hydrogen, or oxymercuration, demercuration, where our electrophile was a mercury, or even bromine and water, where our electrophile was a bromine. But still, a bunch of variations where pi bond reaches out to electrophile, carbocation intermediate, and then a nucleophile comes along. We saw examples where the same atom acted as both electrophile and nucleophile. That was the formation of cyclopropanes and epoxides. And the cycloadditions, where at least the first step of those was all identical, where the pi bond reached out to one end of a molecule, and the other end of that molecule reached back to form another bond, ultimately making a ring. And then the last but not least, we see what I'm still showing here on the screen, the catalytic reduction of alkenes to alkanes with hydrogen and some palladium or other catalyst. All right, that's alkene chemistry in all its glory. Next, we're going to move on to triple bond chemistry, alkyne chemistry. No, this is mostly syn, as I said. All right. So we're going to move on to our next presentation. Thank you. You can predict the products. You should be able to, for these different reactions, be able to predict the products and know at least the simplest part of the mechanism, though sometimes I said don't worry about kind of the end game, like part B in this mechanism and this mechanism.